flow for which there is a free surface, that means pressure. Okay, so now when you compare, I like to compare this pipe flow with an open channel flow. So in this case, particularly in an open channel flow, here we have got a free surface which is subjected to atmospheric pressure. So how does the flow takes place in an open channel flow? So when we make the channel bottom sloping in the direction of the flow, there is a component of weight, that is W sin theta, which is developed in the direction of the flow, which makes the flow to take place. So that's about the open channel. That means the classic examples of open channel flow are flow in irrigation canals, maybe flow in rivers, streams or nalas. Then we have navigation canals, power canals, like this. So here the water surface is exposed to atmospheric pressure. So when we want to discuss about the distinction between the open channel flow as well as the pipe flow, in case of an open channel flow has a free surface as we discussed, whereas the pipe flow has no free surface because it is enclosed in a conduit. Okay, in open channel flow the free surface will be subjected to atmospheric pressure, whereas the pipe flow, since it is enclosed in a closed pipe or a conduit, there will be no direct atmospheric pressure, but there will be in hydraulic pressure only. So here when you install the piezometers at different sections of a pipeline, then the depending upon the pressures in the pipeline, the water rises to some level. If you join the water levels, then you get the hydraulic gradient line. But in case of an open channel flow, water surface itself is the hydraulic gradient line. So that's the difference. And the total energy line, as we discussed in Bernoulli's equation, always lies at a distance of v square by 2g above the hydraulic gradient line in both the cases. Now, how does the flow takes place in an open channel flow? Since you know that the pressure at the top surface of the water in a channel is a constant, that means it is subjected to atmospheric pressure. There can be no pressure difference between any two sections. So now, as water flows in the channel, it will always be subjected to resistance. In order to overcome this resistance and to cause the flow of water, the channel is made sloping towards the direction of the flow. So that means a component W sin theta in the direction of the flow is developed, which causes the flow of water in the channel. But in pipe flow, there is always a difference of pressure between any two sections, and that is known as the pressure gradient, and hence the flow takes place. In the pipes, the cross section of flow is fixed. Generally it is round because it is defined by the geometry of the conduit, and the cross section of the pipe is generally round, but that of open channel may vary from circular sections to irregular forms of a natural streams. So coming to the kinds of an open channel flow, the channel flow can be classified as a natural channel or artificial channels. So natural channels includes all water courses which they exist naturally on the earth. They have irregular shapes, sections of varying shapes which is developed in a natural way. The examples are rivers and streams. So artificial channels are those channels which are constructed by the human effort. So they have cross sections of regular geometrical shapes like rectangular, trapezoidals, circular, etc. So navigation canals like power canals or irrigation canals or roadside gutters are few examples of an artificial channels which are built by human effort. So generally artificial channels are prismatic. The prismatic in the sense that they have same shape along its length and laid at a constant bottom slope. So now coming to the types of flow, we have what is known as steady flow and an unsteady flow. So here in this case of a steady flow and unsteady flow, time is the criterion. So flow in an open channel is said to be steady if depth of flow doesn't change with respect to time interval under consideration. Then flow is unsteady if depth of flow changes with time. So therefore in steady or unsteady flow, the time is the criterion. Okay, in the case of a uniform or a non-uniform flow, so we have the space as the criterion. So if an open channel flow is said to be uniform if depth is same at every section of the channel, and flow is varied or non-uniform if flow changes along the length of the channel. So in case of a non-uniform flow or a varied flow, they are classified into two types, like rapidly varied flow and gradually varied flow. the flow is rapidly vary if depth suddenly changes over a very short distance. Example is hydraulic jump. And if depth gradually changes over a very long length of the channel, then it is classified as a gradually varied flow. Example is the backwater curve. So coming to laminar and turbulent flow. So here the flow is laminar if the viscous force are strong relative to the inertial force. So in laminar flow, the water particles appear to move in definite smooth paths or streamlines, and thin layer of fluid seems to slide over an adjacent layers. And if there is if the water particles move in irregular paths, which is in a zigzag manner, or which is neither smooth nor fixed, then it is known as turbulent. Here the viscous forces are weak related to the inertial forces. So it is always classified based on Reynolds number. If Reynolds number is less than 500, then it is laminar flow. If it is between 500 to 2000, then it is transitional flow. If it is greater than 2000, then it is turbulent flow. So coming to subcritical, critical flow and supercritical flow. So it depends upon the Froude's number. So if Froude's number is equal to 1, then it's known as a critical flow. If Froude's number is less than 1, then it's subcritical flow. And if Froude's number is greater than 1, it is the supercritical flow. So generally the gravity force predominates here. The effect of gravity upon the state of the flow is represented by ratio of inertial force to the gravity force, which is known as a Froude's number. So based on Froude's number, so these types of flow has been classified. So we have what is known as a geometric elements of a channel sections. So these can be defined entirely by the geometry and also the depth of the flow. So these are extensively used in the flow computations, and that's why we have discussing what is known as the geometric elements of channel sections. So here in the first case of the various geometric elements of a channel sections are, so depth of the flow. So depth of the flow is represented by y. Okay, it is the vertical distance from the lowest point of a channel section to the free surface. So this becomes the depth. So that means here in the rectangular section, this is the lowest section, this is the free surface. So vertical distance from the lowest point of the channel section to the free surface is known as a depth of flow. Similarly here also it is, this y is the depth of flow. So what is top width? So top width is the width of the channel section at the free surface. It is not this width, not of the channel, it is the width of the channel section at the free surface. So here also it is the width of the channel section at the free surface. Similarly this will be the top width. So what is water area? Water area or wetted area is the cross-sectional area of flow, is a cross-sectional area of flow taken normal to the direction of the flow. So that means if you cut at right angles to the direction of the flow, so whatever the cross-sectional area that you get will become the water area or the wetted area. So this will be A, B, C is nothing but the area. Similarly in this case it is B into Y. Similarly here also this trapezoidal section, this part becomes the water area. Okay, so now wetted perimeter. So wetted perimeter is the length of the channel boundary, in contact with the flowing water. So it is not the total length like this of the channel section, it is the length of the channel boundary in contact with the flowing water. So therefore wetted perimeter is AB plus BC. Similarly here it is Y plus B plus Y. Similarly this sloping length plus B plus the sloping length only up to the free surface. Okay, so it is the length of the channel boundary in contact with only with the flowing water. So that is the wetted perimeter. Similarly, we have the hydraulic mean radius. It is the ratio of water area or wetted area to the wetted perimeter. So that R is A by P. And hydraulic depth D, capital D, is the ratio of water area to the top width. Similarly, section factor Z is the particularly for the critical flow computation is the product of the water area into the square root of hydraulic depth. And section factor for the uniform flow computation is the product of water area and hydraulic radius to the 2/3 power. So that is the section factor for uniform flow, whereas section factor for this is for the critical flow computation. So coming to the whatever we discussed about the geometric elements will apply to standard channel sections. We'll take a simple case of a rectangular section. So we have a rectangular sections of a bottom width B, and so depth of flow is Y. So now you can say that why this is depth of flow, because it is the vertical distance from the lowest point of the channel section to the free surface. So this becomes Y. So therefore given B and Y, so now the next geometric element was the top width. Top width, the width of the channel section at the free surface. So this becomes the top width, so which is definitely equal to B. So T is equal to B now. So wetted perimeter is the length of the channel boundary in contact with the flowing water. So it has to be here Y plus B plus Y. So it is B plus 2Y. So what is water area? It is the cross-sectional area of flow taken normal to the direction of the flow. So therefore it is B into Y. So what is hydraulic mean radius? It is A by P. So that is A is B into Y, whereas P is B plus 2Y. And hydraulic mean depth is the ratio of water area to the top width, which is B into Y by B equal to Y. So this is very important in the case of a trapezoidal sections. Now we take a trapezoidal sections of a bottom width B and side slope say 1 in Z. So for one vertical it is Z horizontal, and let Y be the depth of the flow. So why this is Y? Because it is the vertical distance from the lowest point to the free surface is Y. So given B, Y and the slope, that is one vertical to Z horizontals, so then we can calculate what is the top width. So top width for the trapezoidal section is nothing but the width of the channel section at the free surface. So it becomes AD. So width becomes AD, which is if you divide into triangles and rectangle, so we get this top width as AE plus EF plus FD. So now what is EF? So for one vertical it is Z horizontal. For one vertical it is Z horizontal. For Y vertical it will be ZY horizontal. So therefore AE distance will be ZY, whereas FD also will be Z into Y. So okay, so now EF is equal to this B. So therefore top width has to be B plus ZY plus ZY, which becomes B plus 2 times ZY. Okay, so Z is nothing but the horizontal the horizontal corresponding to one vertical, so you have to be very careful in calculating the value of Z. So what is wetted perimeter? It is the length of the channel boundary in contact with the flowing water. So therefore it will be AB plus BC plus CD. So therefore, so now you know that for calculating AB, so this is ZY, AE is ZY, whereas BE is Y. So therefore this AB is root of ZY whole square plus Y square. So Y square is common into 1 plus Z square, taking out of the root, so it becomes Y. So AB is nothing but Y into root of 1 plus Z square. Okay, so therefore it is B plus 2 times Y into root of 1 plus Z square is the formula. So therefore you can remember this formula for the wetted perimeter, which is nothing but this is the total length. So it is B. So each length is Y into root of 1 plus Z square. This is also Y into root of 1 plus Z square. So therefore it is B plus 2Y root of 1 plus Z square. So now water area. So water area is the cross-sectional area of flow taken normal to the direction of the flow. So it is the area AEB plus EBCF plus CFD. So now you can calculate this area, which is half ZY into Y, okay, plus B into Y, this area, plus half ZY into Y. So that gives, so there's this formula as, so Y into B plus ZY. So you can remember this. So this is okay, so it is 2 times, so therefore it will be ZY square, okay, ZY square. So Y comes out of the bracket, so it will be B plus ZY. So hence water area is Y into B plus ZY. Now coming to the circular sections. So circular sections here we have, okay, so suppose the free surface is somewhere here. The free surface can be at the center line or below the center line or above the center line. So we can derive the formulas for each of the geometric elements. So let the angle subtended between the radius, okay, be theta. So therefore, when you put a vertical line here, it divides into theta by 2 and theta by 2. So this is R is the radius to the free surface. So R is the radius. So OA is R, whereas OB is R. Okay, R is the radius. So you know that CD becomes Y because it is the vertical distance from the lowest point to the free surface. So CD becomes Y. So given the value of R and Y, so we are able to find out and then the angle subtended theta. So we are able to find the various geometric elements. Now coming to top width. So top width is the width of the channels section at the free surface. So that becomes AB. So whereas AB is nothing but AD plus DB. So what is AD? So taking sine theta by 2, sine theta by 2 is AD by R. So therefore AD becomes R sine theta by 2. So therefore it is R sine theta by 2 plus R sine theta by 2, which gives 2R sine theta by 2 as the top width. So what is perimeter? So perimeter is this arc length. It is the length of the channel boundary in contact with the flowing water. So ACB is nothing but is the wetted perimeter. That gives, if theta is the angle subtended and R is the radius, so R into theta gives this perimeter. Okay, so theta should be in radians. Similarly, what is water area? So water area is the cross-sectional area of flow, so taken perpendicular to the direction of the flow. So therefore the area ACB gives the water area. This is this area. So therefore now you can have this sector like OACB minus the triangle gives this area. Okay, so area of a sector, so complete area we should take. Okay, complete area minus the triangle gives this area. So therefore the entire sector area, that is OACB, is half r square theta minus this triangle. Okay, that is half into 2r sin theta is the base. Here this distance is r cos theta by 2, because you can find out from cos theta by 2 is base by hypotenuse. So therefore this distance has to be, OD has to be r cos theta by 2. So it is minus half into 2r sin theta by 2 into r cos theta by 2. So that gives half r square theta minus half r square. So here, so this r and r is r square. So 2 sin theta by 2 cos theta by 2 can be written as sin theta. So half r square is common. So hence you can remember the formula for the water area as half r square into theta minus sin theta is the formula. So what is depth of flow? Depth of flow is only this DC. Okay. So therefore that gives OC minus OD. So what is OC? It is nothing but the radius. So therefore radius minus this OD gives the depth, which is r cos theta by 2. So r minus r cos theta by 2. So r into 1 minus cos theta by 2 is the formula for the depth of the flow. Hence, if you are able to find the angle theta, the various parameters like top width, which is given by 2r sin theta by 2, or the wetted perimeter, which is given by r theta, or the water area, which is given by half r square into theta minus sin theta, or the depth of flow, that is r into 1 minus cos theta by 2, can be determined. So these are the various geometric elements that has been discussed in the introduction to the open channel flow. So now coming to the basic aspects of the next topic, which is the uniform flow. So you know that I already told in types of flow that what is uniform flow. So uniform flow is which always the space is the criteria. So when the depth of flow does not change from section to section, okay, then it is known as uniform flow. For example, if the depth here, if when you go for different sections here, the depth of flow remains same, which is y. Here also it is y. Here also it is y. So since the depth of the flow is same, so water area has to remain. If B is, if suppose it is a rectangular channel, the width is B everywhere, prismatic channel. So therefore water area will be B into y throughout. So if the water area is same, then the discharge or the velocity has to remain same from section to section. So therefore, so when you know that the water surface is a hydraulic gradient line, so therefore and since velocity is same, so v square by 2g is same throughout here, so therefore your energy line also will remain parallel to the water surface. So in this case, when the water surface is parallel to the channel bottom, because the depth of flow remains constant, the water surface is parallel to the channel bottom. That shows that energy line here, which is drawn at v square by 2g above the hydraulic gradient line, energy line, or as well as the water surface or hydraulic gradient line and the channel bottom are all parallel to each other. That means the slope are all equal. That is, energy line is represented by SF. Okay, should be equal to SW, which is the slope of the water surface, which should be equal to the slope of the channel bottom, which is S0, that is taken equal to S. Henceforth, in uniform flow, whenever I say S, that is the channel bottom slope, or we also call it as a longitudinal slope or a bed slope of the channel. So we'll discuss about the uniform flow formulas. So first is the Chassis formula. So now here we have considered a uniform flow. So here two sections are considered for a length L, where V is the velocity of flow, Y is the depth of the flow. So therefore, if you should take any section here, so it made any general section is taken which has got a water area and a wetted perimeter. Okay, so it can be a rectangular channel, it can be a circular channel, it can be a trapezoidal channel. So that's why a general shape is taken. And now if theta is the angle made by this channel bottom with respect to horizontal. Okay, so this is the sketch, the representative sketch showing the uniform flow to derive uniform flow formulae. Now the Chassis formula is derived mathematically from two assumptions. So you know that whenever the flow takes place, there is always a resistance to the flow. So the resistance of the flow comes from the bed as well as from the sides of the channel. So here it is assumed that the force resisting the flow per unit area, okay, per unit area of the stream bed on the sides is proportional to the square of the velocity. So therefore, the force resisting the flow is proportional to area of the bed and the sides, okay, and square of the velocity is proportional to the square of the velocity. So therefore the force resisting per unit area, so don't bring this bring it here, force per unit area is proportional to v square, so taking area of stream bed and sides on this side and taking out the proportionality sign, so hence it is made equal and introducing a proportionality constant. So it will be K. What is the area of the stream bed and sides? It will be simply the perimeter into the length. It is not the water area. It is the area of the bed and sides. So area of the bed and sides is nothing but the perimeter into the length. So that is the part of that which is resisting the flow. So therefore the part of the area which is resisting the flow. So therefore it is P into L. So this V square is there. So it is, so that's why this is the resisting force which is denoted as K V square PL. Now for uniform flow, the see here, whenever we have the sloping theta, so there is a weight component which is acting vertically downwards. So this, it will be at an angle theta with respect to the normal to the bed. So therefore this component is W cos theta, but this component is W sin theta, which is responsible for flow to take place. So therefore, so whenever the flow takes place, the component of weight of water in the direction of flow, that is W sin theta, has to be equated to kV square PL. Okay, the resisting force. So therefore then this water surface will assume a constant depth. So therefore a component of weight of water in the direction of flow is calculated, which is W sin theta. What is weight of water? It is specific weight into volume. Okay, so what is specific weight? It is omega or W, and the volume of water is nothing but area into length. So that is the volume of the water. So area into length. So sin theta, because theta is very small, so sin theta is equal to tan theta is equal to the slope, which is nothing but S, as we have discussed earlier. So therefore it is equal to W A L into S. So now according to second assumption, so the component of weight of water should be equal to the force resisting the flow. So equating this two equations, so we get, so V square should be equal to W by K, A by L and L cancels out, A by P S. So here, so now V is equal to root of this, so root of this entire term. So but A by P is nothing but hydraulic mean radius, and this specific weight is a constant, K is a constant, replaced by another constant known as the Chassis constant. So therefore the formula A to calculate velocity of flow in the channel section is V is equal to C root RS. There are various formulas to calculate Chassis constant. So therefore, Chassis constant is also given by Gangulet-Coulter formula, which is given by 23 plus 0.00155 by S plus 1 by capital N divided by 1 plus, so in bracket 23 plus 0.00155 by S, close the bracket, multiply by N by root R. So here N is known as the Coulter's N. So okay, generally Coulter's N varies from 0.01 for a very smooth surface to 0.035 for the earthen channels. So for cement concrete finish, it can be taken equal to 0.015. So here hydraulic mean radius you will be able to calculate by A by P. The bed slope will be given to you. So only thing is the Coulter's N. If Coulter's N is given, then you should put here and calculate Chassis constant, and then go for V is equal to C root RS to calculate the velocity of flow. So therefore, you have to be very careful. So here, when Coulter's N is given, it should be used to calculate C and then go for V calculation. Sometimes the Bessen's formula will be given, where Bessen's constant will be given like M. So that C Chassis constant is given by 157.6 divided by 1.81 plus M by root R, where M is a Bessen's constant. Here it varies from 0.11 for a very smooth surface, okay, smooth cement surface, to 3.17 for the earthen channels. However, for a concrete finish, you can take it equal to 0.21. So therefore, if Bessen's constant is given, you are able to, and also by given the sections, you can also calculate hydraulic mean radius, and that will enable us to calculate the constant C, and then you put it in the Chassis equation to calculate velocity of the flow. Now we have the other formula to calculate velocity of flow, called the Manning's formula, which is an empirical formula. So is V is equal to 1 by N, R to the power of 2 by 3, S to the power of half, where N is known as a Manning's roughness coefficient, or also known as Manning's rugosity coefficient. This value of Manning's N is similar to the value that is given by the Coulter's N. So but if the Manning's N is given, use it in the Manning's formula to calculate velocity. If Coulter's N is given, calculate using Coulter's N, calculate C and put it in the Chassis, equation, V is equal to C root RS. So don't mix up Manning's and Coulter's N in the problems. So generally you should not use this equation. However, if what is the relation between Chassis constant and Manning's N is that you know that V is equal to C root RS and V is equal to 1 by N R to the power of 2 by 3 S to the power of half. So if for the same velocity, then you can equate these two equations. So therefore, here S to the power of half, S to the power of cancels out. So you are left with 1 by N. 2 by 3 minus half is 1 by 6. So therefore, Chassis constant can also be written as 1 by Manning's constant, R to the power of 1 by 6. Sometimes if the Darcy's Weisbach friction factor is given, then you are able to calculate C, which is given by root of 8G by F. G is acceleration due to gravity, and F is a coefficient of friction. Okay, so that will enable you to calculate C, and then you take this C and use it in the Chassis equation to calculate velocity. So it is root of 8G by F. Whenever the flow takes place, there is an average shear stress, that is the resistance can be always calculated, so which is given by specific weight into hydraulic mean radius into slope, so which is WRS, where specific weight of water is 9810 Newton per meter cube. R is hydraulic mean radius in meters, and slope, you know, longer slope or bed slope will be given, so that will give the average shear stress, okay, which is given in Newton per meter square. So these were the various concepts and the formulas that were discussed with respect to uniform flow, and so we have some few problems to solve. So that means the very purpose of solving this problem is to understand the geometric elements of various channel sections like rectangular, trapezoidal, and circular channels, and also if problems are given on triangular channels also, you should be able to calculate. So the basic concepts of all the geometric elements is to be understood, and the appropriate formulas have to be used, and also to calculate velocity and discharge we have to know which constant is given, like Chassis constant given, so then you should use Chassis equation. If Manning's constant is given, so then you should use Manning's equation. Sometimes Bessen's formula or Cooter's coefficient are given, so that will enable you to calculate Chassis constant and then use Chassis equation. So these things you should bear in mind before we solve the problems. Now it is given that a rectangular channel, so that is 2.5 meters wide. A rectangular channel 2.5 meters wide is given. So it is a rectangular channel, so remember. So then carries water to a depth of 1.2 meters. So y is 1.2 meters. Bed slope of the channel is 0.0036. So bed slope is given. So that is yes. Here it is given that Chassis constant is C is equal to 50. So C is 50. So we have to calculate what is velocity of flow and the discharge. So now you know that we have, since Chassis constant is given, so we have to use Chassis equation. So therefore we are using Chassis equation, V is equal to C root RS. So for that we need R. So that's the basic geometric elements are calculated. So what is area? It is B into Y. Okay, so therefore 2.5 into 1.2, which gives 3 meters square. Similarly, wetted perimeter is the length of channel boundary in contact with the flowing water. So therefore it is B plus 2Y. So that gives, so B is 2.5 plus 2 times 1.2, that is Y. So therefore we get 4.9 meters. So therefore hydraulic mean radius is the ratio of water area to wetted perimeter. So therefore the hydraulic mean radius is calculated. So substituting in the formula in Chassis equation, V is equal to C root RS. So then we get C multiplied by root of R is 0.6122 into S is 0.0036. So which gives 2.35 meter per second. Similarly, you know the discharge is area into velocity. So that gives the discharge in meter cube per second. So a very simple problem to start with. So given the width and the depth of the flow and longitudinal slope, so we are able, and Chassis constant, so we are using Chassis equation. Similar to the previous problem, we have the a rectangular channel. So rectangular channel 3.5 meters width, so B is 3.5 meters. It laid at a slope of 1 is to 2000, so 1 is to 2000. So therefore it is okay. So you can divide by 2 to 1 divided by 2000. So you have to calculate what is the normal depth of. So normal depth of flow is nothing but uniform depth of flow, that is Y. So we have to determine Y. So the discharge is given here. So Q is given and Manning's n is given. So since Manning's constant is given, so we should use Manning's equation, and also we have to calculate what is the velocity of flow. So since depth of the flow here, so it is like this. So here we have, so this is B and this is Y. Okay, so now area is nothing but B into Y. Area is B into Y. So therefore B is given, which is 3.5. So 3.5 into Y. So like this. So now wetted perimeter is B plus 2 times Y. So 3.5 plus 2Y. So similarly you take the hydraulic mean radius as area divided by perimeter. So which gives 3.5 times Y divided by 3.5 plus 2Y. Now since the discharge is given, so discharge is area into velocity. So Q is area. So because Manning's equation is given, Manning's constant is given, we have to use Manning's equation. So 1 by n r to the power of 2 by 3 s to the power of half. So substitute the values of Q as 5 meter cube per second. Area is 3.5 times Y. So 1 by n is 0.02. Here R we have already calculated. So like this in the form of equation. So like this. Okay, raise it to the power of 2 by 3 into S is given, which is 1 is to 2000, raised it to the power of 0.5. So now we get, you can solve this equation by means of your calculators. So therefore we have simply solved like this the equation. So now I'll do by trial and error. I'll assume various values of Y till left hand side is equal to right hand side. So for this equation I have tried various values. So finally I found that for 1.48 I am getting left hand side as 1.92, right hand side as 1.92. So therefore the value of Y is 1.48. So you can also use this equation and put various values of Y here, so till you get 5 as the answer. So 5 meter cube. So therefore you should try various values of Y till you get answer Q, which is 5 meter cube per second. So by this, if you put 1.48 in this equation here, you will get 5 as the answer. So therefore that means that the depth of flow is 1.48 meters. So now you know area. Okay, you know area because the width is known and the depth of flow is known, hence area can be calculated. Therefore the velocity of flow can be calculated, which is q by a. So that is 5 divided by 5.18 gives 0.965 meter per second. So therefore here there is a typical problem where determination of normal depth, since y is not known, it always involves trial and error. But nowadays you are using calculators which will give the if you substitute the equations, it is giving direct values of y. So no need to do like trial and error, but it solves. So, and generally here I gave in the problem as a normal depth of flow. Normal depth of flow is nothing but the uniform depth of flow only. That means you should find out the value of y. So one more problem to calculate. Okay, so again for rectangular channel, so we have given rectangular channel at 2.5 meters. It is laid on a slope of 0.005, has discharge of 10 meter cube per second. Then the depth of flow is given as 1.2. So here what would be the discharge? So as the depth changes, the discharge also changes. So that's the reason why we should go ahead with the calculation, the first set of calculations. But only thing is nothing is mentioned about the constant. So whether to use Chassis constant or Manning's constant. For you can try with Manning's. I have tried with the Chassis constant. So therefore I am using Chassis constant and finding C. Okay, so finding Chassis formula and finding C, and this C, because it remains constant, I will use it for the second set of the data. Okay, so therefore now for the first set of data, so I want to find out what is the value of C, because the value of C is not given here. Okay, so area is nothing but B into Y, so 2.5 into 1.2, which gives 3 meter square. So therefore we have wetted perimeter, which is length of channel boundary in contact with the flowing water, so it is B plus 2Y. So B is 2.5, whereas Y is 1.2 meters. So therefore it gives wetted perimeter is 4.9 meters. Now taking the ratio of water area to the wetted perimeter, so we get the hydraulic mean radius. So since the area is known, and as well as discharge is known, you can find out the velocity. Okay, so now use it in the equation V is equal to C root RS. Otherwise you can use Q is equal to A into V and substitute. So still we have calculated what is velocity and then used velocity equation, that is C root RS. In this case C is unknown, so therefore C can be determined, and this C is used in the second set of calculations. Now what happens to the same channel if the depth of flow is now reduced to 0.8 meters? Okay, so since the width of the channel section remains the same, which is 2.5 meters, so therefore it is 2.5 into, now this depth is 0.8 meters. Do the calculations with 0.8. So similarly the perimeter is also calculated, which is B plus 2Y, so therefore this, okay, so we have 4.1, and hence hydraulic mean radius is calculated, which is A by P. So now making use of C, which you had calculated in the previous, because it remains constant as 60.24, so we have R as the new value. Okay, so hence you can calculate the velocity. Okay, velocity. So velocity now becomes 2.975 meter per second. So using this 2.97, you can find out the discharge. That is what asked. So therefore, the discharge now becomes 5.95 meter cube per second. So this is how for the depth of flow, which we had earlier case we had calculated, and because the C constant was not given, we used the data for calculating C. Now when the depth of flow is reduced to 0.8 meters, since C remains constant, so we are using it for the second set of the calculations, where all other terms remains the same, like B remains the same, yes, bed slope remains the same. Only since depth of flow changes, area changes, perimeter changes, hydraulic mean radius changes, and hence accordingly velocity of flow is calculated, and hence discharge can be calculated by area into velocity. So rectangular channel, again we have 3 meters wide, carries water to depth of 1.5 meters. So here I had not solved a problem on bottom slope, so therefore now the bottom slope is unknown, so we are using, so since Manning's n is given, so Manning's equation is used. So discharge is given as 12 meter cube per second. So given B 3 meters, given Y 1.5 meters, discharge 12, meter cube per second and n as 0.015. So again go for the same calculations here. Manning's equation, so Manning's equations is used. Manning's constant is given, so we are using Manning's equation. So area, as you know, it is b into y, so 3 into 1.5, which is 4.5 meters square. So perimeter is length of channel bound in contact with the flowing waters is b plus 2y, so therefore it is b is 3 plus 2y, that is 2 into 1.5 gives 6 meters. So therefore area is water area divided by the perimeter. 4.5 divided by 6 gives 0.75 meters. So velocity of flow, because discharge is known, area is calculated, so the discharge divided by area gives the velocity. So therefore we can make use in this equation. So v is equal to 1 by n r to the power of 2 by 3 s to the power of half. So knowing the velocity, knowing n, okay, and r, so we can calculate bed slope. So that gives 0.002349. Okay, that you can make it as 1 in there. Okay, so like 1 is to 426. When you divide 1 divided by 426, this becomes 0.002349. So you bring it to the denominator and write this term. So it is now the bed slope is 1 is to 426. So I'm doing various problems on rectangular channel only to give some practice over the geometric elements and to calculate various parameters. So here the width of the channel is 5 meters. Depth is also given, which is 2.3. So Darcy-Weisbach friction factor was given, which is 0.02. So we have to estimate the values of Chassis constant and Manning's N. So now here B is 5 meters, Y is 2.3 and friction factor is 0.02. As usual, since B and Y are given, you are able to calculate water area. So it is B into 5 into 2.3, which is 11.5 meters square. Similarly, wetted perimeter is B plus 2y. So B is 5 plus 2 times 2.3, which gives 9.6 meters. So therefore that gives hydraulic mean radius A by P. So A is 11.5, whereas perimeter is 9.6. So the hydraulic mean radius is 1.198 meters. So now you know the formula for Chassis constant, which gives as 8 root of 8g by f. Root of 8g by f. So g is acceleration due to gravity, which is 9.81, and friction factor is given as 0.02. So therefore Chassis constant is 62. Okay, so if you know Chassis constant, I already found out r. So you know c is equal to 1 by n r to the power of 1 by 6. I had derived the relationship between c and n. So that's why using c here and the r here, so you can calculate the value of n. So the value of n, corresponding value of Manning's roughness coefficient is 0.0165. So this problem will give a relationship between c and n given the friction factor 0.02. So given the channel sections, you are able to calculate the hydraulic mean radius. Using hydraulic mean radius, you are able to calculate n. So next problem is a rectangular channel. Okay, the rectangular channel carries a discharge of 300 liters per second. You know that if you divide by 1000, so you will get meter cube per second, that is 0.3 meter cube per second. So therefore discharge is 0.3 meter cube per second. 1 liter is 10 raised to minus 3 meter cube. So lateral slope is given 1 is to 6250. So therefore divide 1 divided by 6250, which gives this 0.00016. Normal depth of flow is given, that is y is given 0.595. You have to calculate what is the width of the channel. So therefore B is unknown here. So you have to calculate B. Okay, Manning's N is given, so you should use Manning's equation, so 0.018, and also calculate the average shear stress, okay, which is WR into S. So as usual, since the width is okay, width is unknown, so it remains as B. So Y is given, so it is 0.595 B, and P is B plus 2Y, so therefore B plus 2 times Y. Okay, 2 times Y. So therefore you take the ratio A by P, so that gives this equation. So now you know that Q is equal to A into V, because Q is given 0.3, area is this, okay, area is this 0.595 B, 1 by N is given, R is you can substitute this equation, and to the power of 2 by 3, and S to the power of half. So if you will get this equation. Now you substitute by trial and error various values of B till you get 0.3, or you solve this equation and write it like this. Okay, so then you use various values starting from 1. Okay, so finally you find that for 1.5 meters the values are almost the same. So I have just almost approximately they are same, so therefore that is the bottom width of the channel, so that is B. So by trial and error we should calculate various values of B till it matches the equation, above equation. So knowing the value of B and also Y, so water area can be calculated. So water area is B into Y, so that gives 0.8925 meter square. And then we can calculate perimeter, which is P is equal to B plus 2Y. So substituting the value of B and Y, we get 2.69 meters. And then hydraulic mean radius is required for shear stress calculations. So therefore R is A by P, which gives area is 0.8925 divided by 2.69 gives 0.332. And hence average shear stress can be calculated as WR into S, that is 9810 into 0.332 into slope. So we get 0.52 Newton per meter square. So this is how we calculate the average boundary shear stress. So we had solved many problems on rectangular channels. So the now from here onwards we start solving the problems on trapezoidal channels. So now you know that for a trapezoidal channel a bottom width is given. So B is 2 meters, which is given. Side slope is 1.5 horizontal to 1 vertical. So therefore you know that whenever this side slope will be given, so here corresponding Z will be horizontal to 1 vertical. So already the vertical is 1, so Z has to be 1.5. So therefore Z is always H by V. So H is 1.5 divided by vertical, so which gives 1.5. So now your Manning's constant is given 0.018. So therefore, and even the bed slope is given as 1 is to 4000. So knowing the formula for the water area, which is Y into B plus ZY. So knowing the value of Y, B, Z and Y, so we are able to calculate water area, which is 5.74 meter square. So wetted perimeter is length of channel boundary in contact with the flowing water, which is B plus 2Y root of 1 plus Z square. So therefore substitute the values of B, Y and Z. So you will get the wetted perimeter. So now the hydraulic mean radius R is A by P, which is 5.74 divided by 7.048, which gives 0.8144 meters. So now velocity of flow is given by 1 by n R to the power of 2 by 3 s to the power of half. So knowing the values of n is 0.018, so R is already calculated. Substitute the value of R, okay, and then the slope is 0.00025 raised to the power of half. So you get the velocity of flow as 0.766 meter per second. So therefore the discharge can be calculated as area into velocity, which comes to 4.4 meter cube per second. So this is how you calculate. For here you have to be very careful, so that water area equations and the wetted perimeter equations have to be carefully taken. So this problem we are calculating trapezoidal for a trapezoidal channel where the bottom width is given. Okay, so now the bottom width B is 10 meters, side slope is 1.5 horizontal to 1 vertical, so therefore it is H by V, which is 1.5 divided by 1, so therefore Z is 1.5. Discharge is given, which is 100 meter cube per second. Depth of flow is given, so Manning's n a constant is given, so that's the reason why we are using Manning's equation. In this case, we are trying to find out what should be the bottom slope. So what should be the bottom slope? So that's the okay, so this is wrong, we should not write this. So we are trying to find out the bottom slope. Okay, so now first step is to calculate what is the water area, because B and Y is given. So Y into B plus ZY, so therefore that gives water area as 43.5 meters square. Next, knowing B and Y, we can also always calculate the wetted perimeter. So wetted perimeter is B plus 2Y. So root of 1 plus Z square. So root of 1 plus Z square. So therefore we get a perimeter as 20.82 meters. So hydraulic mean radius can be always calculated as the area divided by perimeter. So 43.5 divided by 20.82. So that gives 2.09 meters. So similarly, discharge is 100 meter cube per second. Area is calculated as 43.5. So that that gives the velocity. So using the equation, velocity is equal to 1 by n r to the power of 2 by 3 s to the power of half. So velocity is known, okay, and n is given 0.015, and r is already calculated, so that is 2.0896 to the power of 2 by 3, and s is unknown, so therefore s can be calculated from this equation. So therefore it comes to 0.000445. So taking to the denominator, it is 1 is to 2246. So therefore the bed slope for this particular problem is 1 is to 2246. So coming to the next problem for the trapezoidal channel again. So bottom width is 3 meters, bottom width is 3, and side slope is 1 is to 1. Again h by v is 1 by 1. So therefore here z is 1. The bottom slope is given to you 0.0036, and discharge is given, which is 15 meter cube per second. So, and depth of flow is again 1.25. You have to find Chassis constant. So all quantities are given. So only thing is Chassis constant is to be determined. So Chassis equation is to be used. So now same problem, water area y into b plus zy. So knowing y 1.25, knowing b 3, z as 1. So you can calculate area, which is 5.3125. Similarly, wetted parameter is b plus 2y root of 1 plus z square. So therefore you are able to calculate the wetted perimeter. So there is wetted perimeter. So knowing water area and perimeter, you can calculate hydraulic mean radius, so which gives 0.81 meters, and hence the discharge is given, which is 15 meter cube per second. So divided by area gives the velocity, which is 2.82. So knowing velocity, and hence r is also known, and slope is given, so you are able to calculate the constant, Chassis constant, which comes to 52.2. So that's how various parameters are given and Chassis constant can be calculated. So next problem is to for the trapezoidal channel, the bottom width is given. Okay. So bottom width is 3 meters and slope is 1 is to 5000. Bed slope is 1 is to 5000. Side slope of the channel is 2 horizontal to 1 vertical. So therefore it is h by v. H is 2 and v is 1. So therefore z is 2. Then discharge is given, which is 3.1 meter cube per second, and Manning's constant is given as 0.024. You should calculate what is the velocity of the flow, and also here it is required to calculate the normal depth of flow. So whenever I said that if anywhere the normal depth of flow is to be calculated, that requires trial and error. So now y is unknown in these problems. Okay, so y into b plus zy. So b is given, z is 2. So there is y into 3 plus 2y. Similarly, in the wetted perimeter, y becomes unknown. So therefore b is known, 3 plus 2y root of 1 plus z square. Z is 2. So therefore that gives as 3 plus 4. 0.472y. So now you can know area in terms of y and perimeter in terms of y. So you can substitute here and get hydraulic mean radius in the form of equation that you substitute in the Manning's equation. So q is a by b, but b is 1 by n r to the power of 2 by 3 s to the power of half. So since q is 3.1, area is this. Okay, area is this. Substitute here. Then 1 by n r to the power of 2 by 3 and s to the power of half. So solving this, you put various values of y so that you will get 3.1 as answer by trial and error. Otherwise you can solve this equation like this and then go on putting the value of r. Still left hand side is equal to right hand side. So in this case I got somewhere nearer to that, 22.5. So therefore the depth of the flow has to be nearer to 1.2 meters. So taking depth of flow as 1.2 meters, we can calculate the area. Substitute here. Okay, depth of flow, so you will get area 6.48 meters square. So discharge is known, which is 3.1. So 3.1 divided by 6.48 gives 0.48 meter per second. So that's how it involves whenever depth of flow is involved. So it is the trial and error procedure. Now a trapezoidal channel is designed to convey 50 meter cube per second. So therefore discharge is 50 meter cube per second, the velocity of 2 meter per second. So since discharge is given, velocity is given, you can calculate area. Okay, so area is discharge divided by velocity, so 25 meters square. So now the side slope is 1:1, so z is 1. Manning's constant is given 0.02, and only here in this case you have to the bed width to depth ratio is given, so b by y is given, so ratio is 8. So making use of this ratio, you can solve the problems. So now, since the discharge is given and velocity is given, so you are able to calculate area. So now area, you know, formula y into b plus zy, but area is known, which is 25 meters square. So y you keep it as, but instead of b, you can write it as 8 times y. So 8 times y plus z is 1, so 1 times y. So that gives 9y square. So 25 is equal to 9y square, so y can be calculated. So y will be 1.67 meters. So therefore, knowing y, you can always calculate b, which gives us 13.34 meters. So bed width is calculated, depth of flow is calculated, so we require bed slope. So that's the reason why we are going for the calculation of, because area is known, we have to go for, because knowing b and y, you can calculate perimeter, which is b plus 2y into root of 1 plus z square. Hence it enables us to calculate hydraulic mean radius, which is 1.385. So use the Manning's equation. So v is equal to 1 by n r to the power of 2 by 3 and s to the power of half. So hence the bed slope can be calculated, which comes to 1:965. A trapezoidal channel has a bottom width of 3 meters, so trapezoidal channel is 3 meters. Side slope is inclined to 30 degrees to the horizontal, so therefore it is given like this. Okay, so this is 30 degrees. So this is 30 degrees. So now we are required to find out the one is to z. So this is 1 in z. Okay, if this angle is theta, then this angle is also theta. So you know that tan theta is 1 by z. Tan theta is 1 by z from this calculation. So therefore you can calculate z value, which is 1 by tan theta, which is, so you can use this z value in the calculations. So that is the only change. That's why I took this problem. So I have to estimate the Manning's coefficient and average shear stress. So now knowing all the values, we can calculate water area. So water area is given by y into b plus zy. So therefore y is 1.5. B is 3, Z is here 1.732 into Y. So that gives the water area. Similarly, the wetted perimeter can be calculated by B plus 2Y root of 1 plus Z square. Okay, Z square is here. So therefore that gives 9 meters. Next, hydraulic mean radius is R is equal to A by P, so that gives 0.933, and hence since the discharge is known and the area is calculated, so you are able to calculate what is velocity. So using velocity, V is equal to 1 by n r to the power of 2 by 3 s to the power of half. So velocity is calculated already, so n has to be determined, so therefore n is 0.025 because we know R and slope. So you know to calculate the average shear stress, which is given by specific weight R into S. So specific weight is 9810. Hydraulic mean radius is calculated as 0.933 into bed slope is 0.001. So that gives the shear stress as 9.15 Newton per meter square. So another problem of trapezoidal channel, which has got a bottom width of 2.5 but inclined at 60 degree to the horizontal. Again same thing, tan theta is 1 by z and tan 60, that is z is 1 by tan 60, which gives 0.5773. So this value is to be used for z. So similarly b is given, y is given, and bed slope is given. So discharge is also given. So you are okay. Okay, so here discharge is given for first set of calculation when normal depth is 0.5 meters. You should calculate the new value of discharge when it is 0.7. So you have to use Manning's formula. So therefore n has to be calculated. So the first set of calculation, n is not given. So we are calculating n. So now we know depth of flow as 0.5. When the depth increases to 0.7, discharge also increases. So corresponding 1.5 will increase to something else. So therefore for the first set of calculations, 1.5 meter cube per second is given. That will enable us to calculate n. So using this n for various set of data, then for depth increases, we can find the new discharge. So therefore water area is y into b plus zy. So therefore knowing y, knowing b, knowing z, and y. So we can calculate water area. Similarly, the wetted perimeter can be calculated, which is b plus 2y into root of 1 plus z square. So r can be calculated as a by p. So then the velocity is q by, because discharge is 1.5 meter cube per second, so dividing by the area we'll get velocity. Now you can use the formula v is equal to 1 by n r to the power of 2 by 3 s to the power of half. So that gives the Manning's constant. So Manning's constant is 0.022. Now we can use it for the second set of data. B remains the same, z remains the same, bottom slope remains the same, only the depth of flow changes. Calculating, so b remains the same, 2.5 meters, and y is 0.7. So similarly s is also known, so therefore z is 0.573. So therefore water area is calculated using the new depth, which is 0.7, so it comes to 2.033 meter square. Similarly, the wetted perimeter can be calculated as b plus 2y root of 1 plus z square. So knowing the value, that is y is equal to 0.7 meters, so therefore the wetted perimeter is 4.117 meters. So therefore hydraulic mean radius is a by p, which is calculated. So then using the formula Manning's equation, so v is 1 by n r to the power of 2 by s to the power of half. So you can calculate 1.27 meter per second, and hence the value of discharge when the depth of flow is 0.7 can be calculated, which is 2.58 meter cube per second. So now coming to the problems of circular severe pipe, which is here you have to find the size of the circular severe pipe. So that means you have to find the diameter or the radius. Okay, so here we can find the diameter or radius. Okay, so now here the discharge is given, so which carries 1.1 meter cube per second when flowing half full. That means it is this, like this, exactly half. So Manning's n is given, so Manning's n. So now when the pipe is running half full, so this will be the angle theta for you, that is it will become 180 degrees. So theta is taken as 180. If you want to use the formulas that are there, so otherwise you can use area as pi r square for the circle, pi r square by 2, so which comes as same thing. Pi r square by 2 is nothing but pi d square by 8 in terms of diameters, and wetted perimeter is nothing but r into theta, is half the circumference. So that is theta is nothing but 180 into pi by, so which is pi d by 2. Okay, so same thing, so which is okay, pi 2 pi r. So 2 pi r is the entire circumference, half the circumference is nothing but pi d by 2. So now hydraulic mean radius is a by p, so therefore it is d by 4. So now you know discharge is a into v, so discharge is 1.1, area is known as pi d square by 8, 1 by n, r to the power of r is d by 4, to power of 2 by 3, s to the power of half, hence Saul says d is 2 meters. So therefore the diameter of the circular sewer pipe has to be 2 meters. So now the only thing is the formulas for the water area is half r square into theta minus sin theta, or the perimeter is r into theta. So these two equations have to be used to solve the problems. So coming to the next problem of circular sewer pipe, here circular sewer pipe is 0.8 meters in diameter. Okay, 0.8 meters in diameters, conveys a discharge at a depth of 0. So depth is point. So since the diameter is 0.8, radius is 0.4. So that means since the depth of flow is 0.3, it has to be below the center line. So now your free surface is here. Okay, so now from the center, if you join to the free surface, that becomes the radius. Okay, so bed slope is given 1 in 900. You have to estimate the velocity of flow and discharge. C is given as 50. So now my aim is to find out the value of theta. So this is the value of theta. So to find out theta, so this will be theta by 2. So now here this is 0.4 and depth of flow is 0.3. So this distance is 0.1. 0.4 minus 0.3. So using cos theta by 2, which is base, which is 0.1 divided by radius 0.4. So therefore this is radius is 0.4. Okay, radius is 0.4. So therefore this gives theta as 151. So less than 180 degrees, so it is below the center line. So which is 151. 0.045. So that is how you calculate theta. Now using the various the value of theta for various parameters. So water area is half r square theta minus sin theta. So half r is 0.4 square. Theta should be in radians, so 151.05 into pi by 180. Pi radians is 180 degrees, so to multiply by pi by 180 minus sine of 151.05 will give 0.1722 meter square. Wetted perimeter is r into theta. Theta is 151, convert into radians by multiplying by pi by 180. So we'll give perimeter as 1.054. So similarly, hydraulic mean radius is 0.1634, which is area divided by the perimeter. So because the Chassis constant is given, we are using Chassis equation C root RS. So that gives the velocity. So and the slope is also given. So therefore we can again use the velocity in discharge. Q is equal to A into V. So that gives 0.116 meter cube per second. So this was the problem where the depth of the flow was less than the radius. So therefore the free surface will be below the center line. Okay. So now circular pipe of diameter 1.2 meters is given. So capital D is 1.2 meters, carries a discharge of 0.4 meter cube per second. Okay, so the diameter is 1.2, so radius is 0.6. So now the pipe is laid at a slope of 1:2. You have to estimate the depth of the flow. So in this case, the depth of flow is involved. That means theta is not known. In the previous problem, theta, we were able to calculate theta because the radius and depth of flow were given. In this case, the radius is given, but we are not able to calculate the angle theta, and hence we need to find out the depth of the flow. So that's how the problem goes. So now as usual you can use the equations like this. Water area is half r square, so let it be below the center line, above the center line, but the equation remains the same. So it is half r square theta minus sin theta. So r is given as 0.6, so half r square 0.6 square, so that comes to 0.18 theta minus sin theta. Similarly, perimeter, whether whatever may be the wherever may be the free surface, it is r into theta. So theta is the angle subtended between the radius, so it's 0.6 theta. So put it in hydraulic mean radius as A by P, so you will get like this. So now you have to use the Manning's equation, so that's why Q is equal to A into 1 by N R to the power of 2 by 3. So knowing discharge, that is 0.3, and hence area is known as 0.18 into theta minus sin theta. So you have to substitute N, then you have to substitute R here. Okay, so that in form of A by P, then yes, so you will get this equation. I have solved this equation, so that just take this as simplified. Otherwise, you for various values of thetas, you should see that it matches. Left hand side should be equal to right hand side. So now I have got for 208 degrees, so therefore theta is 208 degrees. So in this case you see that, or you can put 208 here. So that means be careful that it has to be like 208 into pi by 180, close the bracket, raise to the power of 2 by 3, multiply by 4.435, so you should get 10.48. Similarly, when you substitute here 208 into pi by 180 minus sine of 208, then close the bracket, raise to the power of 5 by 3, you should get 10. Since both are equal, otherwise you have to substitute the values of theta till you get 0.3. So wherever theta is there, only theta is there, you should not forget to multiply by pi by 180 to convert into radians. So you have to be very careful in solving this such type of problems. However, y is equal to r into 1 minus cos theta by 2, so therefore we get 0.745. So here water area, as usual, you can substitute the value of theta. So here I multiply by pi by 180, and that gives the area. Similarly, velocity of flow can be calculated. So here in this case, when you have like this, so this is the center. So here this is how this. So this is what sorry, like this. This is the radius. So this value is theta. So because it is greater than 180 degrees, so this is 290. So when you take area, so half r square theta minus sin theta, theta you substitute 298, then you will get this answer. Okay, similarly, if you take you take r value and multiply by theta, 208 into pi by 180, you should get the perimeter. So like this, you are able to. So in the previous case, we got less than 180 degrees, so it is below the center line. So this is how you can identify where the free surface is there. So now depth of flow is definitely more than the radius, say 0.745. R is 0.6. So therefore depth is this value is 0.6. Okay, this value is 0.6. So because this is the radius, but we have found y is more. So y is greater. So like this, the various problems have been solved. So for rectangular channel, trapezoidal channels, and also this. Also, many problems are solved to just to get a grip, a very idea about the geometric elements of various cross sections of open channel flow, such as rectangulars, trapezoidals. You can also solve problems on triangulars. I also solved problems on circular channels, because circular channels are also classified under open channel flow if it is subjected to the free surface. You should not run full. Then if it runs full, then becomes a pipe flow. In this case, it is either running 3/4 or running half or running 1/4, and therefore it is the top surface is a free surface which is subjected to the atmospheric pressure. So that's the reason why it is classified under open channel flow, and we have solved some problems on open channel flow. Hope you have understood about Chassis equations or a Manning's equation, where to use, when to use, and the various geometric elements were more specifically concentrated in this type of problems. So it is finally that you have say three or four problems you have to practice, so that you get the hold on the equations that have to be used. Hope you had a very good session, and these type of problems will be particularly useful for your competitive examinations like GATE or engineering service exams, or any technical test that you appear for your interviews in a reputed companies. So definitely that's why it was done in an exhaustive manner, so that you will have the total grip over the entire formulas that have to be used. Hope you had a nice session. You just go through any of the yeah, all the problems and the concepts that I had done on, particularly on the uniform flow. And the next session I will more concentrate on the most economical channel section. It will be a very interesting one. Will come out very soon about the most economical channel sections, and this particular this sessions will be always uploaded, will be definitely uploaded on YouTube, and you can subscribe to my channels, and you will be able to see all my videos on various topics that I have done, particularly in the subject hydraulics and hydraulic machines. Thank you.